Evaluating an estimator, bias and variance, let X be a sample from a population specified up to a parameter theta, and let D equals to D of X be an estimator of theta. To evaluate the quality of these estimators, we can measure how much it is different from theta. That is D of X minus theta to the square, but since it is a random variable, it depends on the sample. We need to average this over possible X and consider R of D theta, the mean square error of the estimator D, defined as R of D theta equals to the expectations of D of X minus theta to the square. The bias of the estimator is given as B theta of D is equals to the expectations of D of X then minus theta. So if B theta of D is equals to 0 for all theta values, then we say that D is an unbiased estimator of theta. For example, with X to the T drawn from some density with the mean mu, the sample average M is an unbiased estimator of the mean mu because expectations of M is equals to the expectations of the summations of X to the T summing for index T divided by N. If we take out the 1 over N, there will be 1 over N times the summations of expectations of X to the T summing for index T. And by definition, that will be the expectations of X to the T if we summing for all T. That will be N times mu. And divided by N, because that's outside of the summation symbol, which is equals to mu. This means that so on a particular sample, M may be different from mu. If we take many such samples xi and estimate many mi equals to m of xi, their average will get close to mu as the number of such samples increases. M is also a consistent estimator, that is, the variance of M is approaching 0 as n goes to infinity. So the following is the formula. The variance of M by definition is equals to the variance of the summations of X to the T summing for index T, then divided by N. We take out all those N squared. There will be 1 over N squared times the summations of the variance of X to the T, then summing for all index T. Okay, by the definitions of the variance of X to the T, there will be N times rho squared, then divided by N squared. So that means the variance of M is equals to rho squared divided by N, as n the number of points in the sample gets larger, then M deviates less from mu. Let us now check S squared, the MLE of rho squared. S squared by definition is equal to the summations of X to the T minus M to the square summing for index T divided by N, which is equals to the summations of X to the T to the square summing for index T, then minus N times M squared, then divided by N. So the expectations of S squared, such a variable, is equals to the summations of expectations of X to the T to the square summing for index T minus N times the expectations of M squared, then divided by N. Given that the variance of X is equals to the expectations of X squared minus the expectations of X then to the square, we get the expectations of X squared is equals to variance of X plus the expectations of X then to the square, and we can write that expectations of X to the T to the square is equals to rho squared plus mu squared, and the expectations of M squared is equals to rho squared divided by N plus mu squared. Then plugging this in, we get the expectations of S squared is equals to N times rho squared plus mu squared minus N of rho squared, N times rho squared divided by N plus mu squared, then divided by N. So we take out all the N. There will be N minus 1 divided by N times rho squared, which definitely is not equals to rho squared, which shows that S squared is the biased estimator of the rho square. N divided by n minus 1 times S squared is an unbiased estimator. However, when n is large, the difference is negligible. This is an example of an asymptotically unbiased estimator whose bias goes to 0 as n goes to infinity. The mean square error can be written as follows. D is short for d of x. R of d theta is equal to the expectations of d minus theta to the square, and if we expand the term, that would be the expectations of d minus e of expectations of d plus expectation of d. We just minus it, then we add it back. Then minus theta, as usual, to the square. If we expand the following term, that will be the expectations of d minus the expectations of d to the square, plus the expectation of d minus theta, then to the square, plus 2 times the expectation of d minus theta, then times the following terms, d minus the expectations of d. And we can separate these 3 terms as the following summation: expectations of d minus the expectations of d, then to the square, plus the expectations of d minus theta, then to the square, plus 2 times the expectations of the following terms, the expectations of d minus theta times d minus the expectations of d. Okay, now we have 3 terms, but the last term is a little bit complicated. If we do some simplification, that will be the follows: the expectations of d minus expectations of d to the square plus the expectations of d minus theta to the square plus 2 times expectations of d minus theta times the expectations of d minus expectations of d. Okay, so if we simplify the following, we will get expectations of d minus the expectations of d to the square, which happens to be the variance, plus the expectations of d minus theta to the square, which happens to be the square of bias. So the 2 equalities follow because expectations of d is a constant, and therefore expectations of d minus theta is also a constant. And because the expectations of d minus the expectations of d, which is equals to the expectations of d minus the expectations of d, which is equals to 0, so the last term was just cancelled out. And in equation 4.11, the first term is the variance that measures how much, on average, di vary around the expected value, going from one data set to another. And the second term is the bias that measures how much the expected value varies from the correct value of theta, figure 4.1. We then write arrow as the sum of these 2 terms, the variance and the square of the bias. That is, r of d theta is equals to the variance of d plus b theta of d, then to the square.